Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work for this particular problem. We want to determine the equilibrium position as well as their stability, the equilibrium positions and their stability. To determine the equilibrium position, we will take the derivative of the potential function given, which is 10 cos, okay, cos 2 theta, okay, plus 25 sine theta, okay. So we'll take the derivative is Joe. We'll take the derivative of this, the first derivative, and set it to zero and determine the equilibrium position. While for the stability, we will plug in the equilibrium position into the second derivative, all right, of the potential function to determine stability. All right, so for the equilibrium position, we are going to have this, okay. We're going to have dv, so it's going to be dv the theta. So if we do that, go to zero, we'll have this to be minus 20 sine 2 theta, sine 2 theta plus 25 cos theta. So as I said earlier on, we'll set it to zero, equal to zero. And of course, we know that sine 2 theta is the same thing as 2 sine theta cos theta. So in any case, so this one will now become minus 40, okay, sine theta, okay, sine theta cos theta plus 25 cos theta, 25 cos theta. So that's what we're going to have there, equal to zero. So if we, this one is the same thing as cos theta is equal to minus, okay, cos theta minus 40, open that, have that sine theta, okay, plus 25, okay. So if you look at this, we are going to arrive at cos theta is going to be cos theta equal to 0. Therefore, theta is equal to 90. When we take the arc cos, it will give us 90 degrees, all right? And sine theta is going to give us sine theta will give us, when we sub what is there, sine theta is going to give us okay, 25 over 40 over 40, which is equal to 0.62625. All right, so when you take the arc sine rather, you're going to You're going to arrive at theta to be equal to 14 point, sorry, at 8.68 degree, 38.68 degrees. Okay, so I've been able to get this. Okay, and of course, we can also determine theta, the other one, to be equal to 180. Okay, 180 degree minus 38.68 degree. Okay, 8.68 degrees, which is going to give us 141.32 degrees. So these are the equilibrium positions. Okay, now for the stability, we'll take the second derivative. Stability. So if we take the second derivative, it's going to give us the squared v, the theta squared. Okay, so that we'll have it to be. So when we do that, we are going to arrive at minus 40 cos 2 theta. 2 cos 2 theta. Okay, plus, sorry, minus 25 sine theta, minus 25 sine theta. Okay, so when we plug in our various values, when theta is 90 degree, theta equal to 90 degree into the second derivative, what we just did now. Okay, we have the squared v, the theta squared is going to be equal to 15. Okay, you can see that this is greater than 0. So for this position, it's stable. It's a stable equilibrium. Stable. And we also consider when using theta to be 38.68 degrees. So we are going to have the squared v, the theta squared. So we are going to have it to be equal to minus 24.37. So you can see that this is less than 0, so the equilibrium is unstable at this position of 38.68 degrees. Then we can also look at when theta is equal to 141 141.32 degrees. We're going to have this to be equal to minus 24.37 minus 24.337. Okay, and you can see that this is also unstable. So these are the equilibrium positions and their stability. Stability is